Screencast 18.10 Gibbs free energy and phase transitions. Oh, let's imagine we're melting some ice, and let's say we are at exactly 0 degrees Celsius to an infinite number of decimal places. So we're right at that perfect cusp where it's between a solid and a liquid. Technically, I suppose it would be neither. Another way of saying it is that we're at equilibrium. There is no spontaneous move in either direction towards melting or towards freezing. That means the free energy change is 0. And when the free energy change is 0, some interesting things come out of it, right? Here it is looking at it for boiling or evaporating, where the rate of condensation is exactly equal to the rate of evaporation. Did I say that right? They're both happening at the same rate. So we've got a dynamic equilibrium. It's not doing one more than the other. So it is has no change in free energy. There is no spontaneity in either direction. Delta G under those standard conditions is 0. So, since it's equal to delta H minus T delta S, we now can rearrange this formula and solve for any of those three things given the other two. So, we can find out the entropy change of a melting or freezing process given a temperature and a change in enthalpy. And here we go. So, they've got the molar heats of fusion. That's the enthalpy to melt or boil some benzene, which is some fairly yucky carcinogenic stuff. And they have to give you the one other piece. There it is, the melting temperature and the boiling temperature. So we got our delta H and we've got our T, so we should plug in directly to solve for the entropy changes. Just watch out to make sure your units are similar. This is kilojoules, which worries me. This is Celsius, which worries me. So we got to do some unit conversion. Here we are, we're melting. And we have our formula, which we just did from assuming delta G is 0. And we had to make sure we converted from kilojoules to joules. We had to make sure we converted from Celsius, that's our 5.5 there, to Kelvin by adding 273. Ooh, they're not being that precise, are they? Giving us a value of 39.1 joules for Kelvin mole. This is a positive process, suggesting a entropically favorable, random, increasing, less ordered change. And it is, because you're melting. Molecules are spread out, more free to move around. There you go. And when we boil, I'd expect this also to be positive, maybe a lot more positive. Let's find out. Yeah, double or more, so that's good. And it's done by the exact same process. This is Screencast 18.10, Free Energy and Physical Changes.